All right, so today we are going to continue talking about capacitive actuation. In Friday's lecture, we focused mainly on gap tuning. And so by that, I mean our displacements were vertical to make the distance between the plates smaller. Today, we're going to talk about area tuning. Using capacitive comb drives, and then we're also going to talk about dielectric tuning as well. So let's start with comb drive actuators. So we talked about capacitive comb drives earlier in this class when we were dealing with electrostatic sensing. So to recap, we had a structure that looks something like this. Imagine that I have the capability to draw a straight line. So this part up here is going to represent now our stationary electrode array. And then our fingers in between the gaps are going to be our movable electrodes. So I'm now going to indicate some key dimensions on our figure. So we have some distance between our fingers. This is going to be D, and D should be the same on both sides. So this distance is going to be the initial length of overlap. And then this distance is going to be our initial height of overlap, like so. And then what we are going to expect to happen is that if there is a potential difference, actually, let's identify this real quick. So we have some fringe capacitance here, CF. And then we also have some overlap capacitance here, COL. There's going to be some on the left and some on the right, but we'll just identify one of them because they're identical for right now. Excuse me. So sorry, I got something in chat. Can I admit Stephen audio? I don't know that anybody is not admitted. Like I see Stephen phone listed as a participant. And then I also see Stephen Gordon and Tim, which I think all three of those are you. right, I'm going to keep going. All right, thank you. Okay, so so we have our fringe capacitance and we have our overlap capacitance. Okay, so if we apply a voltage drop across our stationary electrode array and our movable electrodes, what we are going to see is a displacement. Technically, there's two options here, but for the way that I've drawn it, we're going to see a displacement in this X direction. So effectively, the movable electrodes are going to be pulled further into the gap between them there. Okay. The other option would be if our electrodes weren't at the same height and our mechanical suspension was oriented in such a way that deflection in the Z or the up and down axis were easier, we might be able to increase the area by moving our plates to where the heights match up. Okay. But the key here is effectively, regardless of the way that we orient this thing, the distance D is going to be the constant value, and either L naught is going to be enhanced by a factor of H, making the plate area of overlap larger, or the initial area of overlap in the height direction will be enhanced by increasing the area of the plates. Okay. So for a single finger, the capacitance is given by epsilon, the permittivity of material, multiplied by L naught plus X divided by the distance. And then we have some contribution due to fringe as well. If we have N overlapped fingers and we neglect the fringe capacitance because it's typically much smaller than the area capacitance because there's significantly less area of overlap, we find that our total capacitance has a displacement dependency as epsilon N H times L naught plus X over D. And really this should be approximately because we're neglecting the fringe. So from here, we can determine our electrostatic force that is generated by our applied voltage. So our electrostatic force Fe as a function of X, much like in Friday's class, will simply be the derivative of the energy stored in the capacitor system, which is 1/2 CV squared. So the force will be the derivative of 1/2 CV squared. And since the capacitance is the only thing changing with X, we're going to have 1/2 the derivative of capacitance with respect to position multiplied by our bias voltage squared, and performing the indicated derivative on the equation above gives us epsilon NH over twice D times the square of our bias voltage. Excuse me. So in some ways, this equation is very similar to what we derived for gap-tuned variable capacitors, okay? So what I mean by that specifically is that our force, our electrostatic force, is always in a direction that will cause an increase in our system's capacitance. So it's always going to pull our movable fingers in further into the gap such that the area of overlap increases. Additionally, because our electrostatic force depends on the square of our bias voltage, the polarity of our voltage is utterly unimportant. It does not matter if we put a positive voltage or positive polarity on the movable electrode or positive polarity on the stationary electrode. Either way, our force that's generated by Coulombic attraction is going to be such that our capacitance increases. Now, the principal difference here between our expression that we derived on Friday for gapped tuned devices and our expression today is that we don't have a dependency on X. So our electrostatic force does not depend on our plate position. Okay. This is actually a good thing because it means we don't have to worry about pull in or anything like that. The larger the voltage that we apply, the larger the force that we get, and for a particular mechanical suspension spring constant Km, the larger the displacement that we get. We don't have to worry about plates snapping together or anything like that, counterbalancing things. We simply have a force that's acting to increase the capacitance. Okay. So let's work an example problem. So let's say that I have a system like so. So this is an anchor on one side of my system. This is an anchor on the other side of my system. And then I have simple mechanical suspension like so. And then down here is going to be my comb drive portion. So this bit is my movable electrode. And then, actually, let me draw this slightly shorter. Not that it particularly matters. Here are my stationary electrodes. And they're all electrically tied together. Like so. So let's call this distance LGB. Let's call this distance WGB. And our entire structure has some thickness T or thickness H that we'll deal with. Let's say that our initial overlap here is L naught. Our distance between the fingers is D. And let's throw some numbers at this. So let's say that the length of our guided beam spring is 200 micron. The width of each of our guided beam springs is 2.5 microns, and the thickness of our guided beam spring is 20 micron. Now, let's say that the original overlap length here is 100 micron. Our gap between fingers is 5 microns. The height of our fingers will also be 20 microns. Let's say that there are 200 fingers for this system and that it is made of polycrystalline silicon using a surface micromachining process, so that we have a Young's modulus of 120 gigapascals. So what I want to know is what bias voltage is needed to achieve a displacement of 5 microns. Okay. Give me just a moment to go find my asthma inhaler. Sorry about that. All right, so what are you guys' thoughts? All right, since nobody's biting, we've only really introduced a single equation here. So we know that our electrostatic force Fe is epsilon NH over 2D times the square of our bias voltage. So I would argue that our bias voltage is going to be the square root of 2D times whatever our electrostatic force is. Let's see, 2D, so epsilon NH here, right? So we know what D is, we know what epsilon is, we know what N is, and we know what H is. So what about this electrostatic force? Well, this is just a mechanical suspension that is being acted on by an electrostatic force, right? So I would argue that Fe is going to have to be equal to Km, our mechanical spring constant, times X, right? Because we want to move that mechanical suspension by some displacement of X by applying this voltage. So the only thing that we don't have to plug into this equation is Km. So let's start first with, does anybody see any flaw in the reasoning here, right? Is anybody paying attention at all?
Sorry, I'm here, but I'm on mobile today.
Yeah. Oh, sorry about that. So let's see what's going on in chat. Don't see any flaws. Great. Thank you, Hayden. All right. So how do we calculate the mechanical spring constant for this system? Well, this is just 2 guided beam springs connected in parallel, right? So Km for this guy is going to be EI over 12 LGB cubed, actually twice because there's two of them. Where I is the moment of inertia here. So that's going to look like 2E. So we are bending in the width direction. So this is going to be TGB times the width cubed. The 12s are going to cancel each other out. LGB cubed. And I get a mechanical spring constant of, 75 over 8 newtons per meter. And plugging that in here and solving for our voltage, we get plus or minus 115 volts and some change DC. Okay. So we can see that for this relatively stiff suspension, it takes a pretty considerable voltage to get some movement out of this thing. Obviously, if we made our springs softer by either making the length LGB longer or the width WGB smaller, we would have softer springs and could therefore achieve a similar displacement for a smaller voltage. Okay. 115 volts really isn't out of the realm of possibilities, at least for what's been used in research. For practical applications, like putting this into some type of system that's really usable, 115 volts DC is rather high. But in research settings, I've seen people use as much as 300 volts to get similar displacements. When we talked about the gapped tuned devices on Friday, we observed that the maximum capacitive tuning ratio was effectively 150%. So we could never get more than a 1.5 increase in the initial capacitance versus the actuated capacitance, assuming that we were trying to avoid pull-in effects. For our capacitive cone drive actuators, the tuning range is really determined by our suspension and the geometry of the system. So if we start off with fingers that only have a small amount of overlap, and then we can generate forces large enough to cause a large displacement, we can get very large capacitive tuning ranges. So for the first few devices that were developed using this scheme, the capacitive tuning range was somewhere around 300%, which is roughly twice as large as we saw for gapped tuned devices. After multiple iterations, that research group was able to get a capacitive tuning range of over 700% with actuation voltages of less than 100 volts DC. So it literally took years of iterating on this basic design in order to get that. So the largest advantage of this scheme, particularly with its applications to radio frequency MEMS and variable capacitors, is that you can get a much more extended tuning range, and you don't have to worry about the pull-in effect. Okay, so the next scheme that we're going to talk about is effectively using dielectric tuning, and it's got some very interesting results. So in order to employ dielectric tuning, there are actually a couple of limitations. So I'm going to draw a picture here. So let's say that we have a plate like so. And its dimension in this direction is going to be A. And its dimension in this direction is B. We also have a second plate down here. Okay. And let's say that we have a material interface here. So everything to the left this guy is material 1, which has some particular relative permeability. And then everything to the right is material 2, which has some different relative permeability. And let's establish a little bit of a coordinate system here. So this is going to be the X direction, and the location of the material interface between the two dielectrics is X. Okay. So how dielectric tuning works is effectively you apply some DC voltage across the plates of your capacitor. And what will happen under certain circumstances is that one of the dielectric materials will be pulled in further between the plates, while the other one is getting pushed out by the first dielectric material. Okay, so in order for this to happen, there needs to be two criterion that are met. The first criterion is that your dielectric materials are immiscible. Let me make sure I'm spelling this right. IMISCABLE. So effectively, this means that they don't mix up with each other, right? So dielectric tuning isn't usually performed with solid dielectric materials. It's often performed with fluidic dielectric materials. And so it's important that the two materials don't like each other or maintain some surface tension when they come into contact with each other so that they do not mix, okay? So that is one criterion. The dielectric materials can't mix. And the second criterion is that at least one of the dielectric materials needs to be polarizable. Okay. So in this case, let's consider what happens if material 1 is polarizable. Okay, so I'm going to draw another simple little picture here. So we have our two plates. Across which we're applying our bias voltage. Because we have a capacitor, we know that we are going to have, actually, let me put here's my interface. Sorry, excuse me. So because we have a capacitor, we know that we have an electric field epsilon like so, that's oriented down. So from the positive polarity electrode to the negative polarity electrode. Because our capacitor is not infinitely long, we're also going to have a fringe field at the edges. Okay. So in previous examples, we've ignored our fringing fields, but here it's actually the fringing fields that are doing all of the work. Okay. So what I mean by that is that if we have a material, so if material 1 is able to be polarized, meaning that it has electrical dipoles, so it will orient itself in the direction of our fringing fields, which will in turn produce a force Fp that is directed into the capacitor. So this force Fp is a polarization force density, where Fp, excuse me here, is the polarization vector P multiplied by the gradient of our electric field vector. Okay. So I believe another way to think about this is effectively the concept of electrophoretic pumping. Okay. So anyway, from the perspective of tunable capacitance, when we have a system like this is like two parallel plate capacitors connected in parallel, where our first parallel plate capacitance has a permittivity of ER1 or epsilon R1 times epsilon naught. And then the area of our first plate is B times X. And then our gap is D. And then our second capacitance is epsilon R2 times epsilon naught. It has an area of B times A minus X over D, like so. So we have two capacitors connected electrically in parallel. So it's simple algebraically add them together, and effectively the areas that the capacitance is, or excuse me, each capacitance is going to see changes as the quantity X changes. So the energy stored by this capacitor as a function of X is 1/2 CEQ times our bias voltage squared, which comes out to be our bias voltage squared over 2. Epsilon naught can also be pulled out. Actually, let's leave that in there for right now. So epsilon R1, epsilon naught, Bx over D plus epsilon R2. That doesn't look like a 2. epsilon naught B A minus X over D. And from here, our force in the X direction is the derivative of our stored energy, which comes out to be V bias squared over 2. So when we take the derivative with respect to X, let's see, can you scroll up to show the figure? Sure. So this is the figure that I'm looking at when deriving this, Stephen. Yep. Am I good to go back down and continue with math? All righty. Excuse me. So when I take the derivative with respect to X of this part right here, I can pull out a factor of epsilon naught times B over D. So epsilon naught B over D, because those are all constants. And so I'm going to have epsilon R1 times X. When I take the derivative, I get just epsilon R1. And on the right-hand side, I'm going to have epsilon R2 times A minus X. Well, when I take the derivative of that, that looks just like negative epsilon R2. So the result here is very, very interesting, okay? It looks very similar to what we saw earlier. It's simple area tuning, just like we saw with our capacitive comb drive here. But the force that's generated is proportional to the difference in dielectric constants of our material. So it depends on the bias voltage squared, which means, once again, the force always acts to increase the capacitance in our system. And in this case, it's also proportional to the difference in dielectric constants. So for any material where epsilon R1 is greater than epsilon R2, that means effectively that the force that's generated is going to try to pull the material having a permittivity epsilon R1 further into the space between the plates and will displace the material having a permittivity of epsilon R2 out, okay? Another very interesting thing about this particular device is its capacitive tuning range, right? So let's assume that epsilon R1 is greater than epsilon R2. Okay. What will the minimum capacitance of this system be? So I would argue that the minimum capacitance of this system when epsilon R2 is less than epsilon R1 occurs when effectively all of the area between the plates is occupied by the second material, or epsilon R2, epsilon naught, A, B over D. The maximum capacitance occurs when the channel between the plates is completely filled with the material having the larger relative permeability or permittivity, excuse me. So epsilon R1 times epsilon naught times AB over D, which means the tuning range of this device is going to be simply epsilon R1 minus epsilon R2 all over epsilon R2, because this is the same as C max minus C min over C min. It's the exact same relationship, right? So the tuning range of this type of scheme is dependent only on the permittivity difference between the two materials. So we get extremely large tuning ranges due to our electrostatic actuation replacing material 2 with material 1, assuming that we have very large differences in permittivity. Okay. So when I did this in graduate school, I was able to get capacitive tuning ranges of over 6,000%. So a 60 times increase in capacitance. So, that is significantly larger than the capacitive tuning ranges that are achievable using mechanical suspensions or mechanical movement of parts. That being said, the biggest limitation here is that the range of applications is pretty low because it takes time to move the fluid in and out of the microchannel. So anyway, all right, so that's what I had prepared for today. So unless there are any questions, I will see you guys on Wednesday, I believe in person for your exam.
Dr. Hartman, do you mind briefly discussing the content of the exam? I know previously we had mentioned we would split the exam in half, with the in-class portion being theoretical and the out-of-class being numerical. Can you kind of just reiterate that, I guess?
Well, you've exactly nailed it. So the in-class portion of the test will be, I haven't decided on the exact number of questions. Let me pull something up here. You guys can see my screen and all that kind of stuff, right?
Yes.
My courses. So I posted this, I think it was early Saturday morning. So these are the 15 different questions that you may be asked on your exam on Wednesday. I will likely just make, I think, 4 different versions of the test, and we'll pull, let's see, let's call it 6 questions. So 6 questions from this list, which is available to you guys randomly, and your job is to answer each of these 6 questions that you're given to the best of your ability. I'm not looking for an essay on each one by any stretch of the imagination. I would argue a paragraph and maybe a picture if you feel it is appropriate to better explain things. For the numerical portion of your exam, you should expect something similar to the level of difficulty of the homework problems that I've given you guys. Any further clarification needed?
I think that covers it.
Doctor,
Yes.
Dr. Horton, I have a question.
Yep.
So, I submitted my homeworks, but I have a few confusion with the solution of my homeworks. So, as the test is day after tomorrow, so is there any way I can run by those solutions tomorrow if you come to the campus?
Yeah, I should have office hours tomorrow after 2 p.m. And I don't anticipate staying home tomorrow. Tomorrow is the earliest day that they'll let me back on, so I very much hope to be there.
All right, thank you, sir.
Yep, no problem.